here we're going to investigate rational functions. All a rational function is, it's a function that's made up of two polynomials that are divided by each other. So these are all rational functions here because you have a polynomial on the top, polynomial on the bottom, or I should say numerator and denominator. And these functions all have some properties that we're going to investigate here. So first of all, let's try to sketch these three polynomials. We might need the assistance of some graphing technology, but first, before we just stick them into Desmos or something, let's see if we can simplify them, because often that makes this much easier. So if you look at this equation, a, we can see that in the numerator we have a difference of squares. We can factor it. And usually the first thing to do when we have rational functions is factor so we can simplify them. Because often we see, just like you see here, we have an x plus 2 in the numerator and x plus 2 in the denominator, and those are both factors, so we can cancel them out. So essentially this equation just equals x minus 2. See that? Now this one we shouldn't need any graphing technology to help us graph, right? That's just the equation of a line. So what I want you to do now is graph that line below. So here's the graph at x minus 2. Let's just assume each box represents one unit. So that's the graph of x minus 2. So are we done? Well, sort of. The thing is, we graphed x minus 2, but that's not actually the function that we're supposed to be graphing. We're supposed to be graphing this function up here at the top. What's the difference between this function and this function? They actually, if we simplify them, they look like they should be equal to each other. Well, the answer is, the one difference between the two of them is that there is a restriction on this. What's the restriction? Well, look at what we did. We canceled out this plus 2 in the denominator. Is there a restriction there? X cannot equal what? Negative 2, right? Because if x equals negative 2 in our initial graph, it's going to end up making the whole thing undefined. So even though it's a graph of a line, x minus 2, we can't plug in x equals negative 2 into the function because the function shouldn't exist there. So there is actually a fundamental difference between this graph up here and this graph here, right? And we sometimes lose things when we cancel out. So we always need to make sure to count our restrictions, or to include our restrictions. So x equals negative 2. Oops, did not mean to do that. X equals negative 2 would be down here, right? And the thing is, the function does not exist at this point right here, right? So it's like there's a little gap in the function there. So the way we show that on a graph is we put a nice circle to represent that there's a gap in the function at negative 2. So if we were to write the domain and range of this function, the domain of this function would be x is an element of real numbers such that, actually let's do it. So the domain is x is an element of real numbers such that x cannot equal negative 2. And we could write the range of the function as well. Y is an element of real numbers such that y cannot equal, and we look and that's at negative 4, right? So that's okay. We call this type of gap in a function, we call that a discontinuity, right? It's a discontinuity in the graph. The graph is not continuous because of that. We call this type of discontinuity a hole, and you'll see that underneath. We'll describe that in a second. But see how it looks sort of like a hole? It's basically a little hole in the graph. Let's go to the next question now. Y equals x minus 3 over x squared plus 2x minus 3. Again, we can't graph that just by looking at it. It's a little bit complicated, but we can try to simplify it a little bit. So can we simplify this? X minus 3, we can't really do much with that. But in the denominator, what do you think we can do? It's a quadratic, and maybe we can factor that, right? Two numbers that multiply to negative 3 and add to 2, so I think that should be x plus 3, x minus 1, right? Can we simplify that? Can we cancel anything out? No, not really, right? There's nothing we can cancel out of the top and the bottom. We have a minus 3 and a plus 3, so those don't cancel out. So what is this going to look like when we graph it? Well, we can think of it in the same way that we thought of the last question. What are the what are the restrictions on this graph, right? From looking at the denominator, we know that x cannot equal -3 and 1, right? Because if we did that, our graph would be undefined, right? So are these going to be holes like in the previous question? Well, actually, let's go to Desmos and graph it and see what happens at -3 and 1. So I actually have Desmos right over here, so I'm going to stick that equation in there. So there it is graphed. What do you notice happens at -3 and 1? They're asymptotes, right? So we actually end up having a vertical asymptote here at x equals -3 and a vertical asymptote here at x equals 1. The function exists everywhere between those asymptotes, right? But it does not exist at -3 and 1. So what I want you to think about, and you can just draw a quick sketch on that, on the place you're given over here. Draw a quick sketch of that function, right? It should just look something like that, just a very quick sketch with discontinuities at -3 and 1. So what's different about these first two graphs? I want you to think about that. One has a hole and one has asymptotes. What's different about the algebra that we did between those two that makes it one or the other? Okay, before we answer that, let's go on to the third example and see if we can complete this pattern. Can we simplify this one at all? Well, let's try. In the denominator, I think we should be able to factor that, right? To factor that, two numbers that multiply to 2 add to -3, I think that's going to be -2 and -1, right? So x minus 2, x minus 1. Okay, that's cool. Does anything cancel to the top or the bottom? Nope, absolutely not. But our denominator tells us what the restrictions are, right? So we do have restriction that x cannot equal 2 or 1. So I want you to make a prediction right now. Are 2 and 1 going to be asymptotes, or are they going to be holes, like in the first question? Make that prediction now, then we're going to throw it into Desmos and see what happens. So when I graphed it, it looked like this. That's sort of interesting. I think we actually need to zoom out a little bit in order to see what's actually happening here. Zoom out, zoom out. Ooh, look at that. Oh, there it is. I found it. There's a missing piece that was difficult to see. See that down at the bottom? I'm actually going to change the x-axis here from -2, just to make it a little bit easier to see. -2 to, let's do 5, just to stretch out that x-axis a little bit. There we go. That becomes a little bit more clear. So the answer to that question I asked about what happens at 2 and 1 is that they are asymptotes, right? We have an asymptote at what looks like 1, right? And an asymptote at 2. The graph also does some sort of weird stuff here, right? Like it's coming down and then it's going back up. But for now, let's just focus on the asymptotes. So we have asymptotes here. Let's go back to our question over here. We can draw a very quick sketch, so do that now. So it looks something roughly like that after you've sketched it. So basically, let's go back to that question. How can you tell, just from algebra, or just from simplifying the function, whether something's going to be a hole or something's going to be an asymptote? And the answer is, the fundamental difference between the first question and the other two is in the first question we canceled out those x plus 2's. And whenever we cancel it out, it's like, sort of like that doesn't exist, discontinuity doesn't exist. But we know it does if we go back to the original question. So it's not impacting the shape of the function anymore because we've canceled it out. It's just creating a hole at that one exact spot. Whereas here, we know at -3 and 1, that's going to impact the shape of the function. So that's why we get an asymptote there, because it's still in the final function. It didn't get removed at all. So that's the main discontinuity. A hole occurs when you cancel something out. It's a discontinuity that was canceled out of the original function, and an asymptote occurs just when the denominator equals 0, right, in the final function. So I'll write a note there and you can copy it. So there we go. Hole is where the denominator equals 0 in the initial equation, but was canceled out when simplified, and a vertical asymptote is where the denominator equals 0 in the final equation after you have simplified it. So we've reviewed how we can find vertical asymptotes or holes of a rational function, but we know from experience that often rational functions have horizontal asymptotes as well, right? And horizontal asymptotes actually have to do with the end behavior of the function. So how does the function behave when x gets very, very, very large or very, very, very small? We're more used to quadratics, right? So if we have a quadratic, or not a quadratic, a polynomial, I mean, we can have a polynomial that looks like this, right? And we know to describe the end behavior of a polynomial, we would say in this case, as x goes to infinity, this graph goes to negative infinity, right? And as x goes to negative infinity, this graph goes to positive infinity. So that's how we would describe the end behavior of a function like that. But we know from past experience that if we have a rational function, it might look something more like this, right? Where as x goes to infinity, as our number gets very, very, very large, the function looks like it's approaching, say, 0, right? And as x gets very, very, very small, or a big negative number, it also looks like the graph approaches 0, right? So what this looks like is it looks like it's a horizontal asymptote. But what I want you to keep in mind is that horizontal asymptotes have to do with end behaviors. They're not actually discontinuities, because discontinuities means where the x values are interrupted. So anyways, the first question we can ask is what happens when a function such as this, f of x equals 1 over x plus 1, what happens when x goes to infinity and x goes to negative infinity? So let's just plug in some really, really large values and some really, really large negative values and see what happens. So if I plug in f at 1,000,000, what am I going to get out? If you do that on your calculator, you end up getting something along the lines of 0.000009999 blah 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 blah, repeating. So essentially 0.000001, right? So let's look at this number. This number is very, very, very small, right? It's approximately equal to 0, right? Very close to 0. What happens when we plug in negative 1,000,000? What's going to happen here? If you do that, you're going to get something similar, 0.00000010001, or something like that, right? Again, this number is so, so tiny that it's approximately equal to 0. So essentially what we're saying, and then think about this, well, what happens if I plug in a number even bigger? So not 1,000,000, let's plug in 1,000,000,000 or 1,000,000,000,000 or a quadrillion. What's going to happen to this number? Well, if you think about it, that number is just going to get closer and closer to 0, right? Because you keep dividing by a bigger and bigger number. The more you divide by a bigger number, the closer this is going to get to 0, right? So that's why we get this behavior when we look at an asymptotic function, right? Where we get really, really close to 0 here and really, really close to 0 here. I'm actually going to throw this equation into Desmos just so we can talk about it in a little bit more detail. So have a look at what's happening here for this function, right? As x gets very, very, very large, as we move more and more to that way, that number is going to get closer and closer and closer to 0. So we would say the end conditions here, or the end behavior here, would be as x goes to infinity, y goes to 0, right? Because it gets very, very close to 0. And if we're going this way, we can say the same thing, right? As x approaches negative infinity, y approaches 0, right? And I can show you what happens if we zoom out on this graph, right? If I zoom out more and more, look, that number is getting closer and closer to 0. Already at 10 and negative 15, it looks like it's on 0. I can zoom out more and more and more and more. Look at that. It's very, very, very close to 0. Okay, so that's the idea. Often rational functions don't approach infinity or negative infinity as x goes to infinity or negative infinity. They can approach values such as 0. So that's just our first example. Let's go back to the others. So let's see what happens in example 1 here. We're asked to find the discontinuities. We're asked to identify the degree of the numerator and denominator. It'll become more apparent why that's the case a little bit later, but let's just do that first part for now. So looking at this, if we want to find the discontinuities, we have to find where the denominator equals 0, right? So the way we do that is by factoring x over, and this is a difference of squares, x minus 2, x plus 2. My question for you is, based on the previous page, will the will 2 and negative 2, oh, so we know, I'm sorry, let me just do this. X cannot equal 2 and negative 2, right? Because that makes the denominator equal to 0. Are these going to be wholes, or are they going to be vertical asymptotes? What do you think? Well, the question we ask ourselves is, did they cancel out, or are they there in the final answer? And the answer is they are there in the final answer. We didn't cancel out either of these things, so that means they're going to be vertical asymptotes, right? So the discontinuities we have are vertical asymptotes. I just do VA for vertical asymptotes at x equals 2 and negative 2, right? Those are our two vertical asymptotes. Okay, so let's just find the degree of the numerator and denominator. That's going to be more important for horizontal asymptotes later. So the degree of the numerator, we just have an x. So the degree of that polynomial is just 1, right? There's like a little 1 that you can't see here when there's no exponent, right? The denominator is a polynomial with degree 2. Let's now quickly throw this into our graphing software. Actually, you know what? Before we do that, we know how to plot these asymptotes, right? The vertical asymptotes. So let's try to come up with a sketch ourselves, right? So I'm going to plot those asymptotes. So there, I've plotted those two asymptotes. Now the question is, does the function like go down here and then like this and like this? What does that function actually look like between those asymptotes? And it's actually going to be a topic for another lesson. But for now, let's just throw it into Desmos to see what's going to happen. If you want, make a prediction, but we'll throw it into Desmos to see what's going to happen. So wow, that's sort of an interesting looking rational function. Notice how we were right about those asymptotes at negative 2 and positive 2. But let's look at the end behavior of this function. As x approaches infinity, what does y approach? It looks like it's approaching 0, right? It's getting closer and closer and closer to 0. And as x approaches negative infinity, what's happening to that function? It also looks like it's getting closer and closer and closer to 0, right? It's getting creeping nice and close to 0. So let's just sketch this and we'll write down the end behavior on our page. So there it is. I sketched our function and I also wrote down the end behavior. So as x goes to infinity, y seems to go to 0. And as x goes to negative infinity, y also seems to go to 0. Let's have a look at the next problem now. We have a linear function over a linear function, right? The top degree is 1, the bottom degree is 1. We can just fill it out super fast here. The degree is 1 and 1. So again, to find the discontinuities, what should we do? Well, we usually try to factor and find where the denominator equals 0, right? Because that's going to tell us where we have our discontinuities. Can we factor this at all? Can we cancel anything out? Nope, not really. But we can look at where the denominator equals 0, right? So this is going to be where 3x minus 1 equals 0. So that's going to happen at, oh, and this is 3x minus 1 cannot equal 0, right? Because that would mean it's a discontinuity. So we bring that over, we divide, we get x cannot equal 1/3, right? So that is a discontinuity. Now, is this going to be an asymptote or a whole? Again, think about it. It's in our final equation. It didn't get canceled out, so it's going to be a vertical asymptote. So we would do that in here as our vertical asymptote at x equals 1/3, right? That makes sense? So again, let's plot this asymptote, and then we're going to throw it into Desmos and see what the graph looks like. Okay? I'm just going to go straight to Desmos actually now, and I'll see you there. So here's our graph in Desmos. Notice how we were right about that vertical asymptote being at 1/3. I know it's a little bit hard to see, but it makes sense, right? It's just past that 1 mark. We have an asymptote. This is really messy, but you get the idea. At 1/3, we have a vertical asymptote. Now, what's the end behavior of this function? Is it still approaching 0 as x approaches infinity? Well, let's see. So as x approaches infinity, that's supposed to be an x, as x approaches infinity, what does y approach? Does it look like it's approaching 0? See how it looks like it comes up above the axis here? So it looks like it's not necessarily approaching 0. We can actually zoom out even more. So I'm going to do that just by changing the x-axis. Let's go from negative 100 to 100. Negative 100 to 100. I want to leave the y-axis where it is so we can really see what that function is approaching. Okay, going back there. See, we can see as x gets to 100, see how the graph is just above the axis? And as x is at negative 100, it's just above the axis too. We can in fact stretch the y-axis a little bit more too. I'm going to make this go from negative 3 to 3. And we can see, if we move that, we can see it's like approaching a value that's not 0, right? So 1 would be up here. And this value actually ends up being, a little bit of a spoiler here, it's approaching 1/3. And same thing on this side, it's approaching 1/3. So we could say this function is a horizontal asymptote at 1/3. We'll learn how to find that in a few minutes. By the way, it's just a fluke that the horizontal and vertical asymptotes are at the same location. They will not usually be that way. But we can say for our end conditions, as x approaches infinity, y approaches 1/3, and as x approaches negative infinity, y also approaches 1/3. So there it is summarized on your sheet. Okay, now let's move on to the next question. One more here. We want to find where this function has discontinuities and possibly find the end behavior of it as well. So are there going to be any discontinuities here? Well, we always do that by factoring, right? The discontinuities are going to come from the numerator and denominator, though. They're always going to come from the denominator. So the denominator here is telling us that x minus 1 cannot equal 0, right? Or else that function would be undefined. So x cannot equal 1. Do we really have to factor the numerator? Not to find any discontinuities. That might help us for graphing a little bit later, but we're not worried about that right now. So in terms of the discontinuities, is this x equals 1, is that going to be a vertical asymptote or a hole? So again, does it appear in our final equation? Yeah, it does. So it looks like it's going to be a vertical asymptote, right? So we would say it's a vertical asymptote at x equals 1. The degree of the numerator is 2. The degree of the denominator is 1. So let's look at what this is going to look like on Desmos. We have a little bit less to work with this time, so let's just throw it into Desmos and see what happens. Okay, wow, this is a little bit of a different looking function, right? It doesn't look like it has the normal horizontal asymptote. But note, we were right about our vertical asymptote being at 1, right? There is still that vertical asymptote, which we can see. I'm just going to show you with the ruler here. Obviously at 1, right there. So there's a vertical asymptote right there, okay? So putting that off to the side for a second, what's the end behavior of this function? It doesn't look like it's going to approach a value. We can check by zooming out. So let's just zoom out this function like this. Zoom out, zoom out, zoom out. Whoa, look at that. Do you see how it doesn't look like it's approaching a horizontal asymptote at all? It looks like the function just goes up and up and up, right? As x goes to infinity, this looks like it's going up and up and up. And as x is going to negative infinity, this looks like it's going down and down and down. So let's just zoom out some more, make sure that we're not crazy. Look at that. It just looks like it's a line when we zoom out enough, actually. So when we zoom out, we lose that sort of, this excitement that happens in the middle. It doesn't look like the function is approaching horizontally at all. It looks like it's approaching sort of on an angle. And we actually consider this a different type of asymptote, and we call it a slant asymptote or an oblique asymptote because the function looks like it approaches sort of this line as we get closer and closer and closer to infinity. So the line that we're approaching might look something like that, right? So it's like we have a diagonal asymptote, right? So I'm just gonna use my ruler here to create that line. It's not perfect, but you get the idea. Hide that ruler. See, like that? I know at the top it looks a little bit off, but basically what it is, it's an asymptote that's on an angle. So how would we describe the end behavior here? Well, it's sort of like a polynomial, how when x goes to infinity, the graph's going to basically go up to infinity. And when x is negative infinity, the graph goes down to infinity. So it's actually like describing a polynomial in this case. So let's go back to our graph and sketch it. So there we go, there's a sketch, and I also wrote down the end behavior, right? As x goes to infinity, the graph goes to infinity as well, and as x goes to negative infinity, the y values go towards negative infinity. Okay?